doesn't work its way off.
Boa tarde, bem-vindos a mais uma sessão sobre espaço no Pavilhão do Conhecimento Ciência Viva. Esta sessão, onde vamos Chasing Space, vai ser em inglês. Temos dois ilustres convidados que falam nessa bela língua. E temos o apoio da Embaixada dos Estados Unidos em Portugal. Agradeço desde já aqui o apoio da Embaixada para trazer os nossos convidados e pela coorganização desta sessão, e de seguida falarei em inglês. So, good afternoon. We have here with us in this full session to attend. I remind that there are people here, but there are also people following us over the internet, so my welcome is also to them. I also salute especially a large representation of the Portuguese Air Force and also the United States Defense. There are some elements here besides the embassy, so you are all very welcome. I hope that you have the opportunity to visit our exhibitions, which are not just for children, they are on very serious topics like water. So please take this opportunity to visit after the session. And now, without further ado, I'll just briefly introduce our speakers. So we have Heidemarie Stefanyshyn-Piper, who is a former NASA astronaut and US Navy captain. So welcome to the Pavilion of Knowledge. She has flown on two space shuttle missions where she completed 5 spacewalks. Having led 3 of them, she has in total over 33 hours of extravehicular activities, some of them lasting almost 7 hours. Just imagine 7 hours out there in space. She was awarded 3 NASA medals, and well, you can read her extensive bio in our webpage. Then we have also with us Humberto Campins, who is a planetary scientist and expert of asteroids and comets, such an important topic if you want to keep safe on the Earth and not happening to us what happened to the dinosaurs. We really don't want that. So he's a professor and director of planetary science at the University of Central Florida in Orlando, in the USA. He chases asteroids, so comets and other celestial bodies, and conducts scientific research on observatories all over the world. He discovered water ice and organic molecules into asteroids. He worked with NASA, with JAXA. JAXA is the Japanese Space Agency, ESA, the European Space Agency, and to prepare several missions that he's going to talk about. And last but not least, he has an asteroid named after him. So that's quite a medal, quite a medal. I will also present my co-moderator, Miguel Gonçalves, who is a well-known presenter of a very popular astronomy program at TV. So welcome. Welcome, Miguel. It's also the first time that we are together on stage, which is, for me, it's a great responsibility being on stage with Miguel.
Oh, please.
And also this session is, we are giving the floor to NASA, but we are members of Zero Portugal, which is the program that we have in collaboration with the European Space Agency that is called Zero to produce education and teacher supports and resources for schools all over Portugal. So now, Heidemarie, please,
okay.
The floor is yours.
Thank you. And I'll give you the extent of my Portuguese. Olá. I'm very, very excited to be here because I get to talk about one of my favorite subjects, and that's going into space. And so let's get started. And if you are wondering, that is me. That was on my first of 5 spacewalks. Just to give you a little bit of background, this was me in high school, getting ready to graduate and then thinking, what am I going to do with my life? What do I want to do? My parents, neither one of them went to college. Both of them came from Europe. My father's Ukrainian, my mother's German. They emigrated to the United States, had a family, and kept telling us as children that it was very, very important to keep studying and to go into college, and as we say in America, live the American dream. And so that's what they wanted for us. But I didn't know what to do. For me, I looked at, okay, what am I good at? Mathematics was one of them. I loved math, and I didn't know what to do with that. And lucky for me, they were starting to encourage girls to go into engineering. Today, it seems like you talk to any child about engineering, and everybody knows what that is. But when I was growing up, I thought an engineer was a person who drove a train. And my father did work for a train company at the time, so that's probably where I thought that. But I went off to MIT primarily because I applied to the school and they accepted me. It's a very, very good engineering school, so I thought, okay, if they accepted me, that's where I'm going to go study. Schools are expensive. MIT is very expensive, so I had to figure out how do I pay for school, because even though my parents had talked about me and my brothers, I have 4 brothers, all of us going to college, they weren't expecting private tuition. So I said, okay, what can I do to pay for college? And I looked at the military. I thought I could spend 4 or 5 years in the military in exchange for paying for college. And so I looked at the different services, looked at Army, looked at Air Force, and decided on the Navy. I'm sorry, Air Force. Because I thought the Navy had lots of options and things to do. So off I went, and after my first year in school and got to see what am I studying? Okay, I know that. Okay, let's look at the Navy. What am I going to do? And I was convinced that I was going to go fly jets for the Navy. I wanted to be a jet pilot. They had opened up jets for women at the time, and that's what I was going to do. And then right before commissioning, I had my final physical and found out I failed the eye test to become a pilot. So I said, okay, I'm committed to the Navy at this point, so what else does the Navy have to offer? Lots of things. Deep sea diving. I figured I grew up in Minnesota, lots of lakes, I can swim. You know, how hard could diving be? And it is physically challenging, I will say that much. It is physically challenging, it was demanding, but I made it through dive school. I figured, okay, I made it through MIT, got my engineering degree, I can do this. Figured out I can do it, and finished dive school, went out into the fleet, and I actually liked what I was doing. I loved working with sailors, most interesting group of people, especially Navy divers, very ingenious, sometimes a little too ingenious for their officers, but I liked what I was doing, so I stayed in the military. And then I learned about NASA and the astronaut program. And I figured, okay, you don't have to be a pilot. I'm a Navy diver. I have an engineering degree. I actually had 2 of them. I had my master's degree in engineering. So I went ahead and applied. And sure enough, they accepted me. Not the first time. I had to apply more than once. That's when you learn that, you know what, NASA doesn't always pick the right people, or the people the first time. They pick the right people. Oh boy, that's a Freudian slip. No, it's just that, you know, the first year they selected a large number of pilots, the first year that I had applied. So I went ahead and applied a second time. And so sure enough, they accepted me. So off I went. And yes, I went off and I got to do spacewalks. Why? Because found out that at least the training for spacewalks, so I found this out before I went up in my flight, is a lot like diving. We do the training underwater, so I figured, okay, why can't I do this? And when I got selected, I did get to my first space flight. I made 2 flights, or 2 spacewalks. Second time was 3 spacewalks. And before I get too far ahead, this is my second flight. This was back in November of 2008 on the Endeavour.
Yeah, go ahead, Mike. Okay, Fergie, vehicle's in good shape, the weather's beautiful, and so on behalf of the entire shuttle launch team, good luck, Godspeed, and have a happy Thanksgiving on orbit.
Kudos to your team, Mike. It's our turn to take home improvement to a new level after 10 years of International Space Station construction. Endeavour's ready to go.
Copy that. Thank you, sir.
Endeavour OTC, close and lock your visors and initiate O2 flow. That is in work. All right, we'll do it. Get a quick comm check.
So that took you through the first 2 minutes of flight. Liftoff happens when the solid rocket boosters ignite. That's what actually gets you off the launch pads. The main engines do light 6 seconds before liftoff. If the computers detected an anomaly in that 6 seconds, they could shut it down and not light the SRBs. But once those 2 solid rockets are ignited, there's no way to stop the solid fuel, so you are going. As I said, 2 minutes, the solid rockets are expended and they are jettisoned away. They do retrieve them. And we continue up another 6.5 minutes on the main engines. So it's 8.5 minutes from liftoff to being in orbit. Once in orbit, then we can start reconfiguring our spacecraft for the craft that we're going to live in for our duration in flight. We get out of the seats, we get to take the orange spacesuits off. Those are the launch and entry suits that we only wear for launch and entry, because once you are in orbit, it is a fairly controlled environment, even though you're in a spacecraft in a vacuum of space going in orbit around the Earth. But it's not as dynamic as the flight and re-entry, and so if there was an anomaly, that you would have time to react, so you don't need to wear all that protective gear all the time. As I said, once you get out of your seats, it is amazing how different that microgravity environment is from being on Earth. Even though on Earth the only place we get it is in an aircraft. NASA has a zero-G airplane. The current model we have is it's an older DC-9, which is like a commercial aircraft that they can go out. They'll go out and fly parabolas, meaning that they go out, get to altitude. If the plane takes a nosedive, rapid descent, everything inside floats. And they'll do that, but once they get to a lower level, they have to climb back up and continue on. But during that descent portion, for about 20-25 seconds, you get microgravity. That's the only place we can experience that on the ground. Experiencing it for 20-25 seconds at a time is very different from actually living in it and having to do work in it. It takes you a while to figure it out how to maneuver in space. But for most of us, we're pretty good at it, and we adapt. We figure out what we have to do, and then we get ready for our destination, which is the International Space Station. This is how it looks now. This picture was taken by the last shuttle flight that left. When I was flying, my first flight, we were still a construction flight. We had brought up the second set of solar panels on the truss element, so most of the elements weren't there. Between my first and second flight, they had built out the truss and added some of the other laboratories, so it was interesting to go back 2 years later and see how much larger the space station had become and what had been added. But like I said, a lot of the construction we were doing with spacewalks, and we would use the robot arms to attach whatever component or module we brought up to the space station, but then to do the final checkout and installation, it was easier to send crew members outside. This is hooking up all of the cables. You have a power cable, a data cable, cooling cables. All of that is much easier to just have a space astronaut do than to try to make everything mechanized in space. This eventually becomes solar panels, but the solar panels are so large, once they're unfolded, each side is about 30 meters long. Well, you can't take something that size up inside the space station or inside the space shuttle to get it up to space. And so everything is all compact, and then we go out on our spacewalks, get things into place, and then we can drive motors to expand things. That was me on the end of what became the solar panels, and so you get to look over the side and get this beautiful view when you're outside. My second flight, 2 years later, we also had a series of spacewalks, but we weren't doing a construction because we were a outfitting flight. We had a cargo carrier that we brought up with supplies for the inside of the space station. But we had the time available, and sure enough, a repair had to be done on the outside of the space station. Just inboard of the solar panels is a large rotary joint that has 2 drive motors and a series of bearings that rotates 360 degrees so that the solar panels can continually track the sun. After one side had been launched, they noticed that there was a problem with the motors, that they were drawing too much current and there was a lot of vibration. It turns out it wasn't a problem with the motors, it was the bearing surface, which is just the outer edge of this ring, was starting to fail. It was crumbling. And so they put together a repair plan, which basically meant that we had to go out there and take grease to clean up debris, because how else do you clean up metal particles in space when the minute you touch something it all floats away? So you had to capture it. Grease worked really well, it's sticky. Tape doesn't work well in space because when tape gets cold it doesn't work really well, so they don't have good luck with tape. So we found grease worked well. Unfortunately, grease liked to get loose in space because it's well lubricated. If you have any kind of entrapped gases in that grease, when you put them in a vacuum of space, they tend to expand. But what all of this ended up leading to is had a grease leak. And one of the things they warned us about before the flight was to be very careful with this grease. It's dark in color. They didn't want to get excess grease on the outside of the space station. It's going to damage other equipment, or could damage other equipment, could damage our space suits. Even just getting grease on the space suits would be dark spots, which was going to affect heating. So all of this meant don't get grease. I got grease on my hands because it leaked. So why am I telling you all of this? Well, had a failure in space. Now my mind gets focused on a failure, clean it up, because we got to continue the job. We got 6.5 hours planned outside here. Well, as I was cleaning things up, wiping everything off, the last thing I touched was this tool bag. If you remember back in 2008, the lost tool bag in space, that's it. My moment of fame was losing a tool bag in space. The good thing is that it didn't hit anything, so it didn't damage anything. We had another set of tools, so instead of my partner and I working independently, we now had to coordinate and share the remaining grease guns that we had. We had plenty of consumables, so that wasn't an issue. The biggest issue was the fact that, why did I lose a tool bag? Well, when you take things outside, everything is tethered, because in microgravity things float, they're not going to stay where they need to be. We had a big box, about this big, that we took out, there was probably about almost 20 different items in here. Everything was on a hook. It turns out everything was on a hook but this one bag. When I picked it up, I didn't notice that the strap was hanging because I was so focused on cleaning things up, I let it go. And you have that moment that you let something go and you think, uh-oh, can I jump and catch it? The number one rule in space is don't make any situation worse. And at that point, you let it go, you call the ground, tell them what happened, and then you tell them what are you going to do to correct the situation. You can't fix the problem. What are you going to do to correct the situation? And that's what we ended up doing. We figured out, okay, we got 2 sets of tools, we can get the job done, and we did. And yes, I lost a tool bag. But in the end, we got the job done, which is really what was the important part. And if we hadn't gotten the job done, then the space station may or may not have been restored to full capability in a timely manner. But not everything we do in space is going to be very serious. We do get some time to have a little bit of fun. And so this is the front of the space station. And all the pilots love to do their flybys. Gives you some idea of the size of the space station. That's down on the shuttle's mid-deck, and that's usually where the shuttle crew will do our exercise. That's where we pretty much live. I always stress exercise because it's very important in space. At the time, the space station was only 10 crew members, or 3 crew members, 7 of us, so all 10 of us got together for our Thanksgiving dinner. Big American holiday, so just like you have at home. I always say we play with our food just because we can. And one of my crewmates, who was a lot smarter than the rest of us, figured out that using plastic sheets and some tape that he could make a cup that the liquid didn't float out of. So I always challenge when I talk to engineering students is for them to figure out what does the shape of the cup need to be so that the liquid doesn't float out of it. And then we left our patch at the end. That's my fun picture from space. Found out long hair is very impractical. My hair was a lot shorter on my second flight. But the thing that is most amazing in space is looking back at the Earth. As you look back at this planet and realize that it's a very beautiful planet. It's a lot harder to figure out where you are because there's no lines, you don't see borders, it's one planet. And what happens on one side affects what happens on the other side. And so it really stresses why it's so important for us on planet Earth to all work together, because this is our only planet. You look at the horizon and you see that light blue layer, that's our atmosphere. And beyond that is the black of space. It's a vacuum, there's nothing. And realizing the amount of effort and energy that goes into putting people into space, whether it's the 3 people or now 6 people up on space station, or the 7 people on the space shuttle to put us up into space, that's a tremendous effort. And to think that all of humanity is going to get into spacecrafts and blast off to another planet is not something that's realistic, at least not in our foreseeable future. So it really behooves us to take care of the planet that we have. So just finishing up, shuttle doesn't stay up forever, so we have to come back home. So the day before landing is we'll start putting all the equipment away, everything that we took out during the flight, we put it all away. We'll put the seats back in because just like an airplane, we all have to be seated and strapped in for landing. And we get back out our launch and entry suits on landing day. When we get the go-ahead from the ground that it's a go for landing, then we'll start suiting everyone up. We go in order, and this is when it's very important to make sure that everything you had on launch, you put it in the same bag and have it all for entry. Once we get the go for deorbit, they'll command the deorbit burn. The computers will fire the jets for a given time. That starts our deorbit process, and then from that time until we're on the ground is about an hour, and during that hour is strictly the re-entry, which is primarily us coming down in altitude, slowing down in space, or slowing down in speed, and coming to the runway that we've pre-selected. My second flight, because weather was bad in Florida, they sent us to Edwards Air Force Base in California, which is our alternate landing site. And during this whole phase, as I mentioned, we're just slowing down. We have no engines. We're a glider, basically, a very big, heavy glider. And so we get one opportunity to land. The majority of re-entry is done by the computers, but the commander takes over just prior to landing. When we come over the field and we start our descent to line up on final for the runway is right about when he takes over, and we'll typically come subsonic right over the field, and then we'll land. The parachute is there to help slow down once we get onto the runway. Initially, the shuttle did not have a parachute, but they were able to add it so that they could take the stress off the brakes and not have the brakes get too hot. So we'll roll out to the end of the runway. Once we get wheels stop, then it's still about another hour before any ground support crews are able to approach the vehicle. They want to make sure that we've secured all of our systems, because a lot of the chemicals that we use in orbit for running our hydraulic machines and for attitude control in orbit for our jets, they work well as chemical rockets in space, but they are hazardous chemicals, so they want them all secured before anybody approaches the vehicle. Then we're able to get out, and that's when we start our readaptation back to being in gravity. I was very surprised. First flight was 12 days in space, second flight was 16 days, and an additional 4 days in space made it much, much more difficult, at least I felt that way, coming back and just standing up, walking around, getting reacclimated to gravity. But the human body, for most crew members coming back from a shuttle flight, by the third day, most of us are back to our same pre-flight stability. And the reason they know that is because they test us before flight on a tilt table, and then they test us afterwards so they know what our baseline is. Space station crew members that spend 6 months in orbit, they come back, they have a much, much longer recovery period. Many of them are not even up to the point of walking out of the vehicle just because of their readaptation back to Earth's gravity. Just one more slide in there for the U.S. Navy. I did go back to the Navy after I was done flying in space, and like I said, I can't say enough for the U.S. Armed Forces and the folks that we have there. And as I always say, that is my story. And as I look around and I see, definitely when I see a lot of young people, is that I challenge each one of you to figure out what your story is going to be, whether it's in space or in some other industry, because it's amazing what you can do when you put your mind to it. So I hope you guys enjoyed that, and that is my story.
We We now continue with Humberto Campins.
Are there any questions for Heidi?
I think we'll do the questions in the end, so please,
Good.
the floor is yours.
Thank you.
Please prepare your questions for both speakers afterwards. I hope there are many.
I'm Humberto Campins. I've already been introduced, so I will skip some of the things that are in the first slide. But I am delighted to be here. It's my first time in Portugal, and I've been here about a little over 24 hours, and this is an amazing city. I'll be telling you a little bit about how likely is an asteroid to ruin your day, and then go on from there. So I control this. Let's see. Yes. So here's a quick outline of my presentation. I'm going to give you an introduction on impact hazards from asteroids. Then I'm going to tell you about international collaboration for planetary defense, to defend our planet against a catastrophic asteroid impact. And I'm going to give you two examples: NASA's OSIRIS-REx mission and the Japanese Hayabusa 2 mission to two different asteroids, and also the current mission that is a collaboration between NASA and the Italian space agency Licia Cube. So it's DART and Licia Cube, which are now on their way to an asteroid. So how likely is an asteroid to ruin your day? So spoiler alert, not very. I just use the trick to hook you into coming. Although with Heidi's talk, I didn't need to. And it turns out that as individuals, we shouldn't lose any sleep over this, because the probability of an asteroid impacting Earth and causing extensive damage while we're alive is very, very low. So as individuals, we shouldn't worry. However, as a civilization, we must, because impacts that have caused global devastation have happened. For example, the one that caused the extinction of the dinosaurs, and they will happen again unless we can stop them. So the dinosaurs did not have a planetary defense office, which NASA does have. So that's a lesson learned. And it turns out that asteroid impacts can be either eliminated or mitigated. What we need to do first, and we actually have done, is to find the hazardous asteroids before they hit. And we know that at least 90% of the hazardous asteroids have been cataloged, and they are not an immediate threat. However, there are some that we call potentially hazardous asteroids. These objects are not a threat to Earth right now, but in the future, their orbits can evolve in a way that can become a big problem. So two of those potentially hazardous asteroids are asteroid Bennu and asteroid Ryugu. And I'm going to expand on that a little bit. Bennu and Ryugu, a tale of two asteroids. These are very similar. They are potentially hazardous. They're not an immediate threat, but in another 160 years, for example, Bennu could threaten Earth. And they have similar orbits. So NASA decided to send the OSIRIS-REx mission to study Bennu, collect a sample, and bring it back to Earth. And the Japanese Space Agency decided to send Hayabusa 2 to Ryugu, collect a sample. They've already arrived at Earth, and they're studying their sample in their laboratories. Ours is due to arrive in September of 2023. So NASA has a Planetary Defense Office. It's actually called Planetary Defense and Coordination Office. And it includes an international collaboration program for planetary defense. And it is featured in the recent movie, Don't Look Up. And I apologize for some problems with the presentation, but the recent movie, Don't Look Up, actually did feature this office. But that was Hollywood's version. In reality, Don't Look Up, my colleagues at that office in NASA are much cooler than what they were in the movie. So in terms of these two current missions that I wanted to tell you about, OSIRIS-REx and Hayabusa 2, and also DART and Licia Cube. So let me go a little bit into detail on OSIRIS-REx. So here's the OSIRIS-REx spacecraft and the Hayabusa 2 spacecraft. That artist's conception of the Hayabusa 2 was when it was headed back to Earth with a sample, and it's already arrived. OSIRIS-REx picked up the sample from the asteroid and it's on its way back to Earth. And as I mentioned, these two are potentially hazardous, but they're also very interesting because they contain secrets that we want to unveil to understand the early solar system and the possibility of how life might have formed and evolved on Earth and on Mars, in planets around other stars. So they bring us a lot of science in addition to the practical knowledge on how to possibly deflect them if they're going to threaten Earth in the future. So here's the orbit of Bennu. As you can see, the orbit of Bennu is in blue, and Bennu's orbit comes within the orbit of the Earth and goes almost all the way out to the orbit of Mars. Ryugu's orbit is similar. It goes all the way to the orbit of Mars, and it comes in slightly within the orbit of the Earth. They both, Bennu and Ryugu, cross the Earth's orbit, and that's what makes them potentially hazardous. And so here's a sequence of images from asteroid Bennu taken by the OSIRIS-REx spacecraft in December of 2018 when we first arrived there. And here's an image of Ryugu taken by the Hayabusa 2 spacecraft about 6 months earlier, also in 2018. So in terms of OSIRIS-REx, and I'm a member of the OSIRIS-REx science team, so I know most about this mission, so I'll tell you a little bit more about it. Our 4 main themes were revealing solar system history, so bringing back a sample of a primitive asteroid for studying and understanding how asteroids formed and how they may have brought to Earth both water and organic molecules, which may tell us how life formed on Earth. Also mitigating impact hazards, so if one of these asteroids is going to threaten Earth, we want to know the most about them so we know how to deflect them. Enabling human exploration, so if Heidi decides to go back into space, then we are making this possible. In the case of NASA's plans of taking humans to Mars, it is very likely that they're going to have to stop in the moons of Mars, Phobos and Deimos, and they are captured asteroids. And so by studying asteroids and understanding the environment that the astronauts will find, we will be enabling human exploration and developing a space economy. So let me take a little bit of time to expand on this point. Asteroids are can be ideal resources for developing a space economy. The moment that you can mine an asteroid and produce fuel and building materials cheaper than launching them, then you have a very large set of customers in Earth's orbit that would prefer to buy the fuel from you than to launch it. And launching things is very expensive. About 1% or less of what sits on the launch pad makes it to orbit. So if you can provide mainly the fuel, which would be in the form of water that you can separate into hydrogen and oxygen, and also building materials, you could, for example, not only supply the Earth's orbiting satellites with their own fuel, cheaper than launching that fuel, but you could also 3D print some of the structures in space. So we've heard recently about the James Webb Space Telescope, which was a complex structure that had to be folded onto itself and put into this tube and launched into space and then unfolded. And all of this made the project very complicated, and it's been remarkable how well it's worked. But if we could 3D print that structure in space and then launch only the components which we cannot 3D print in space, is going to make those structures cheaper, even more interesting than we could ever imagine, because they don't even have to withstand the gravity here on Earth. So that's some of the interesting promises of asteroid mining. When I was invited to join the OSIRIS-REx team and we were proposing the mission to NASA, I was surprised that we would be only the 4th mission to bring back a sample by NASA from an extraterrestrial sample, so from outside of the Earth. So the first one was of course the Apollo mission. Then there was the Genesis mission, which brought back samples of the solar wind. Then it was the Stardust mission, which brought back dust from the tail of a comet. And now OSIRIS-REx is bringing back samples from a primitive asteroid. So it's quite an honor to be part of only the 4th NASA sample return mission. To remind you where most asteroids are, they're here in green, so most of them are between the orbits of Mars and Jupiter. In red, we have what we call the near-Earth asteroids. Those are the ones that come close to the Earth or cross the Earth's orbit. And they're depicted here, and there's quite a few of them, but there's also quite a bit of empty space. So it's not to be too concerned, because the majority of them can come close to the Earth, but would not necessarily be a threat. In terms of asteroids visited by spacecraft, we have a number of them, visited by a number of different spacecraft. Some of them were en route to other places, like the Cassini mission. And here I've highlighted in red both the OSIRIS-REx mission to Bennu and the 2 Hayabusa missions. The Japanese Space Agency was the first space agency in the world to go to an asteroid and bring back a sample, before NASA, before the European Space Agency, before the Russians. So they deserve a lot of credit. And so most of what we expected from Bennu is what we found. The global properties, the rotation rate, the spin top shape, the composition. So we were quite pleased with ourselves. We predicted everything. And then we got there, and it turns out that indeed a lot of what we predicted was indeed what we found, both for Bennu and Ryugu. So these were the shapes that we had gotten from studying them from the ground, and the details that we got when we got there. But we expected to have on the surface of both of these asteroids areas of coarse sand or pebbles, so basically beachy areas where it would be simple to come down with the spacecraft without any trouble, pick up the sample, and head home happily. So do you see coarse sand or pebbles here? Just to give you a scale, that big black rock on the right is about 4 meters high. So we had to rethink things. So no sandy beaches, nothing like, for example, the coast of Portugal. Nope, nothing. And so we had to change. But by the way, the spacecraft was already there, and it had been designed and built and programmed to go down into a sandy beach and pick up a sample. So we had to change drastically our descent strategy to avoid crashing onto rocks, because our main mission was to bring back a sample, and if the spacecraft crashes, we don't. So we programmed the spacecraft to navigate autonomously and to make course correction as it descended towards the sample. So this technology we inherited from the military, and we were able to adapt it to making the spacecraft fully autonomous and make its own decisions as it was coming down. And this was our plan, and when the artist's conception of this trajectory was done, the spacecraft didn't have, the asteroid didn't have big rocks, and the spacecraft didn't have to worry about those. So we had a slow approach to the surface, touch down to collect the sample, and within 5 seconds move away. And just to remind you of how challenging this was, we didn't have to only worry about our vertical direction. The asteroid is rotating every 4.3 hours, so we had to match the rotational velocity of the surface of the asteroid and come down very, very slowly. So we did so, and here's the sequence of images on October 21st, 2020, as the spacecraft is approaching the surface, and it touches for about 10 seconds this time and fires these nitrogen bottles to fluidize the dust and collect it. And we collected so much sample that the seals weren't quite closing, and we were losing particles. So we had planned this maneuver to measure the mass that we had collected, and we were going to rotate the spacecraft so that we could measure the mass that we had collected. And instead, we saw these particles moving away from our sample head, and every time we could see one of those particles, we said, somebody's PhD thesis is going away. And so we quickly stowed that sample onto the capsule, and we say, we'll know the mass when it gets here. So we put it onto the capsule. That capsule's headed back to Earth, and it will arrive in September of 2023. The Hayabusa spacecraft touched down on their surface twice. They're a lot gutsier than we were. Once you have your sample into your canister, these guys said, oh, why don't we create a crater and go sample that crater that we just created. So they had a really complex mission with shooting a projectile, creating a crater, going down, getting their second sample. It was amazing. Luckily enough, NASA and the Japanese Space Agency have an agreement where we're going to be exchanging 10% of the sample from each side. So we're going to be getting samples from at least 2 asteroids. And I say at least because we have indications that both on the surface of Ryugu and on the surface of Bennu, there are rocks that don't belong there, didn't form with them, came from other asteroids. So we may end up with samples of more than 2 asteroids. But thanks to international collaboration, we will have samples from 2 different asteroids that we can learn from. So what about the DART and Lucia Cube missions? I'll go through them really quickly. DART stands for Double Asteroid Redirection Test. And there's a binary asteroid, and here the perspective shows the primary, which is in the background, and the secondary, which is the smaller one, although it looks bigger in this picture, and the DART spacecraft approaching it. And so Dimorphos and Didymos are a binary system. Dimorphos orbits Didymos, so Dimorphos is a smaller one, and it's ideal for this redirection test. Neither of them are a hazard to Earth, so we're carrying out this test in asteroids that are not a threat to Earth either now or in the future. And NASA's DART spacecraft will impact Dimorphos on September 26th of this year. And Lucia Cube will detach, its riding with DART will detach 10 days before the impact, and it will record the impact. Because, of course, DART will vaporize upon impact. And so here's an illustration of it. Here's DART approaching. Lucia Cube has already detached, and it will hit the smaller of the 2 asteroids, and it will cause its orbit to change ever so slightly. And that change will tell us what we need to do in the future to change an incoming asteroid that is hazardous enough so that it will miss Earth. So in conclusion, planetary defense against asteroid impacts benefits from extensive international collaboration. NASA has worked with the Japanese Space Agency and with Italy's space agency to carry out these missions that are telling us about potentially hazardous asteroids and about testing this impact deflection technique on this asteroid. And I also wanted to say that in the last 6 months, I spent as a Jefferson Science Fellow at the State Department, and I worked at the Office of American Spaces, and I'm really grateful for that opportunity and that experience. And I'm also particularly pleased to be at American Spaces here in Portugal, where we'll be in the next few days. Thank you, and I'll take questions or whenever the moderators decide.
Thank you very much to both. So now we open for questions. I imagine there will be a lot of questions. So, Miguel, do you want to start?
To start provocations?
For example, while we wait for the questions of the public.
So what was your opinion about the Armageddon movie? No, I'm not going there. Straight there, okay?
Actually, I like Deep Impact better. Yeah, and Armageddon was like high school fights in space.
Cowboys in space.
The science advisor for Deep Impact did a much better job.
Yeah.
Yeah.
So I was paying attention to your presentation, and you told us that, well, an asteroid impact on Earth will be a very bad day for our planet. And we know that the largest asteroids are already, we know their orbits, where they are, but we have a little bit of a problem with smaller asteroids, in which, according to numbers from the European Space Agency, we, for example, asteroids with 30 to 100 meters in diameter, we still don't know where are 99.3% of them. So, yes, we are safe about bigger asteroids that can have that can give us global catastrophes, but smaller ones that can have a regional, local impact. We still don't know where they are. And is it true that in the 80s, I know this sounds like I
wasn't even born there.
Yeah, me neither. Me neither. Is it true that in the 80s, the number of scientists that were actively looking for near-Earth asteroids were fewer than the employers of a McDonald's restaurant? Because that's outstanding in the 80s.
I think it's still true.
It's true? It's still true.
Anyway, go ahead.
But about these smaller asteroids, how do we know that we don't know many of them?
It's a good question. And the smaller asteroids are not a global threat, but anything bigger than about 30 meters will make it through the atmosphere. And they can cause quite a bit of damage on a populated area. So those, we're taking this in stages. First, we decided to, or the US Congress funded an effort to identify the ones that would be planet-wide devastation. Mm-hmm. And so we did that, and we did that even sooner than we had expected. Yeah. And now we're moving to new facilities, new spacecraft that will detect smaller objects that could devastate a city and would tell us more about those. The reason why we know approximately how many there are and that we don't know 90-some% of them is because we have a rough idea of the size distribution of these objects by studying many of them. And so for every one that is 1 kilometer, we have so many more that are half a kilometer and so many more that are 100 meters. Mm-hmm. And so we extrapolate, and so that gives us an idea of what it is that we don't know. There is a mission called the NEO Surveyor that would be parked somewhere inside of the Earth's orbit and will be looking out from the sun in the infrared and will be able to detect things that we would never see because they're too close to the sun, mm-hmm. and also because things that will be very dark and not reflect a lot of sunlight, which is most asteroids, and they would also be able to detect it. So that is a proposed mission that NASA may fund and would help a lot in detecting the small ones. Many of you may remember the Chelyabinsk impact in 2013. And a colleague of mine in Canada has estimated that that happens over a populated area about every 2,000 years. So it's not that we don't have to worry about it, but it is a threat that could be mitigated in terms that you could have an evacuation of the area, mm-hmm. but it's highly unlikely that something that Chelyabinsk would happen right over a populated area. That's why we didn't have that any other example of it, because it had to explode just at the right height so that the shock wave would come and break windows. And so a very interesting statistics about Chelyabinsk is that until that point in human history, there were fewer than 10 cases of a meteorite hurting a person. Never killing them, but hurting them. So fewer than 10 people ever affected directly by a meteorite until that day, when about 1,500 people were injured. Mm-hmm. And they were not injured by the meteorite itself. They were injured by the shock wave. And if you're in Siberia in the winter and you see a flash, it's like, oh, light! And you go and go look at what the light is coming from, and then came the shock wave, and the breaking of the windows is what caused the people to get injured.
I asked you this question because I believe that one of the most striking events that we have in the history of the solar system in our times was on July 1994, when we all saw how the comet Shoemaker-Levy 9 impacted on Jupiter. I was just 16 at the time, but I was really aware of that event, and I thought, well, maybe this is the warning event that we need to invest in asteroid detection and deflection, all that, and all those techniques. But all these years are past, and we only now have the DART mission don't you think that the dinosaurs are laughing about us?
Well, maybe we haven't acted as quickly as we could have, but there is a concerted effort and funding for defending the planet, and an example of the Planetary Defense Office at NASA. And NASA's not working alone. It's coordinating with the European Space Agency, with space agencies around the world, and so they actually have drills where they simulate an asteroid threat, and they work with other federal agencies in the US, they work with other space agencies abroad, and they have protocols that will go into place depending on how certain the threat is. So anyway, but I feel somewhat egotistical talking this long when we have an astronaut here.
Anna.
Now, and I have here a question burning, is why is the undersea, underwater, so much used as a space analog? We know that astronauts are trained in swimming pools, and now this fantastic experience of Aquarius.
Well, NASA uses the swimming pool because for spacewalk training, as I talked about the zero-G airplane, and it's not practical to train for a 6.5-hour event, because that's how long our nominal schedule for a spacewalk, and then they'll differ based on what happens outside. But you can't train for 6.5 hours in 20-second increments. That's just not practical. And so the pool that we train in, and we like to call it a training tank, not a swimming pool, and it's actually called the neutral buoyancy laboratory, because when you're neutrally buoyant, so you're in the water column and you're weighed out such that your displacement is equal to your weight, and so you neither float nor sink. And that is the most space-like you can get for long durations. But the big difference is that you are in a pool of water, and there's, gravity and buoyancy are still out there, so when the two forces don't cancel each other, you have to deal with them. And so the water comes into effect when you're trying to just do your work, go about what your tasks are, because now you've got this water, which will dampen out your motions and will make it much harder to start moving, but it slows you down very quickly, as you all know when you try to swim underwater. Up in space is that it turns out that in space you don't want to move fast, because it doesn't take much effort to get started, but you have to stop yourself, and that's when it gets harder to stop yourself, because you always will have some sort of momentum moving. And because of the inertia of a couple hundred pound, even though you may not physically move, you will rotate and things like that. And so when we were up in spaces, our mantra used to be slower is faster, because if you work slowly and deliberately, you would be faster than in the pool. If you moved too fast, it didn't take much to slow you down. But it's just that water environment is the closest analogy. Now, you mentioned the Aquarius habitat. That is a habitat that NOAA, the U.S. National Oceanographic and Atmospheric Agency, maintains off of Key Largo, Florida. And the habitat sits in, I think it's somewhere around 45 feet of water, so 45 feet is what, somewhere 15 meters, 12 meters, somewhere around there, underwater. And it's not so much the depth, that just happens to be a convenient depth to put it at, but the depth is not specific. But once you're underneath there, the habitat is used to study their ocean floor. That's what a lot of scientists, marine biologists will come to study the environment there. NASA uses it as a simulator for other explorations. I was involved in a mission looking at what is possible scenarios, operations on the moon. And so if you treat a habitat that's underwater just like you would treat a habitat that's on the moon, because when you go outside on the moon and you want to go out and do your explorations, there's a certain amount of consideration you have to take to get into your spacesuits, get your tools together, make sure you have everything, go outside, and we would try to simulate that, but instead of going out into a lunar environment, we were going out into the undersea environment, and so our spacesuits would be consistent of getting on whatever wetsuits we needed to put on, and we had all of our scuba gear that we needed to go out, and you go out and you do your work. They would try to have us weighted out so we would be in a moon-like environment. So we would be in, they had us outfitted at one point in a 1/6G, so that yes, you could walk on the bottom of the ocean, but it was 1/6 gravity. So if you took a jump, you would jump up 2-3 meters high with no effort. So it would be more moon-like, and so that's what NASA had done, a series of explorations there. And the one I was on, we spent 2 weeks. It was actually 12 days underwater, and coming back, day-to-day routines felt very much like being on a shuttle mission.
So it's not just the physical experience, but also the psychological experience of confinement, of a hostile environment, having to cope with that, with the dressing suits, special suits.
Yeah, initially NASA was looking at it as a training platform for getting ready for space station, because space station was much different from space shuttles. Space shuttle flights, every minute of your day was pre-planned. And so they would have your entire mission would be scripted out, and you would have all of your tasks laid out. But NASA realized that for a 6-month space missions up on the space station and continuing on for years, that they can't script you for that fine granularity. And so we started looking, okay, let's see what happens down on the habitat, is that we'll give the crews, just like you would on the space station, here's your science experiments for the length of time you're going to be down there. Here's what you need to do. You need to, how you're going to work your days. You're going to talk to the ground. You're not going to have constant communication, especially going, beyond low Earth orbit. You won't have constant communication. And so they built that all into it. But one of the things I found is that all the crews that came back, especially the ones that had space flight environment, is that when you're on a 2-week mission, it was very much like being on the space shuttle. There was one mission was down there for 3 weeks, and they said yes, by the end it was starting to get into the routine of this is what long duration space is going to be like.
Yeah. So and it's tiresome, and you really need to be to have a very special character, especially calm to cope with it. We've been for so long time closed in a small space.
Well, the being in a small environment, enclosed space, is something that NASA looks at. That's a characteristic that's hard to define and yet harder to evaluate on people, to say who's going to be a good candidate for long duration flight, because you may think that, okay, I'm going up for 6 months, I can do just about anything for 6 months, but then some people get up there and find out that no, they have a little bit difficulty trying to cope with that environment. Other people get up there, don't have any issues.
Normally, yeah. And the experience of being for so long, almost 7 hours on a row in a spacewalk, that is more difficult to train. You cannot get the same kind, for example, the incidents with the toolbox, that would never happen in water.
No, because if you did lose a tool in the water, then
you just swim to it.
Well, you don't swim to it. Usually the divers, you have support divers underwater because you can't swim very well in the pool. And most of the tools that you're going to lose are going to be ones that are, the more of the functional tools that are not neutrally buoyant, so they will just sink down to the bottom. And in most cases, it's just that, oh, that's a heavy tool. But, we didn't have to work with, we never had any issues with grease in the pool or anything like that, so we didn't deal, so that, it was a new experience out in space.
So it is very important, if we consider, for example, future possible missions to Mars, to have that kind of training with the potential candidates.
Yes, in Mars, chances are you're not going to lose a tool bag because you have some
Yes,
gravity,
okay.
so
Yes,
so that's not going to be as critical. But a Mars mission is even one step more difficult than spending 6 months on the space station, because right now, because of the distances to Mars, the missions that NASA is looking at they're looking at a 6 months transit to Mars, and then spending about a year on the planet, and then a 6 month transit back. And to be 6 months in a spacecraft and then another year, so it's a 2-year mission that now you're gone for 2 years, which is a little bit longer than...
In terms of survival, but I know that Miguel is burning to make you a question.
I'm going to talk about water, since you lead the question also about water, and talk about the bright side of asteroids and comets. I bet that people will be surprised to know that, astronomically speaking, the Earth is a dry planet. When we compare the total volume of mass of our planet and try to investigate what's the percentage of volume of water in our planet, it's only 0.12%, which is hard to believe when we have the oceans and the beach and so on. And we know that some moons in our solar system, for instance, Ganymedes, the largest moon in the solar system, has a staggering 46% of its volume in water. So, scientifically speaking, we know that water is very common in the solar system. That's one of the great discoveries that we had. And a lot of that water, it's in asteroids and in comets. You know, we have a saying, an expression here in Portugal, when we want to offend someone, we say something like that: you are as stupid as a rock. I used to say that if that's rock, it's a meteorite, I'm cool with that. because it's funny to say that probably most of the water that we have in our planet came from asteroids and comets and amino acids, basics of life.
Yes, we
That's the
believe
bright
so.
side.
Yeah, we look at asteroids because of scientific interest, and they represent both a hazard, like I discussed, and a resource. They can be quite a good source of water, for example, as I was explaining, as fuel for spacecraft, for Earth-orbiting satellites. But what we think happened is that water-rich asteroids and comets impacted Earth early on and brought Earth its water and its organic molecules. In terms of the evolution of the Earth, it went through a period which we call the magma oceans, where the surface of the Earth was not liquid water, it was liquid rocks, it was lava. And if the Earth had any organic molecules, they were burnt at that time. So the Earth cools, solidifies, and that solid crust is now devoid of any organic molecules. And it's impacted with asteroids and comets that bring those organic molecules to Earth. And we don't know what they are, because once life formed, it completely changed the makeup of all the organic material on the surface. And so by studying the molecules, the organic molecules that we're bringing back from Bennu, from Ryugu, we are going to be having an understanding of what was the inventory of organic molecules that existed in those asteroids and existed on Earth before life formed. Today, we don't know how life formed. So it would be very interesting to understand that step from a complex organic molecules to a living cell. And by studying these molecules that we're bringing from these asteroids, it's going to be a big help for that.
But
Miguel, we now have questions from the public.
Yeah.
Hi, I'm Captain Ferreira from Portuguese Air Force. I'm sorry being in my CVs. My question for Heidemarie was, I wanted to ask two questions. What were the biggest takeaways, both professional and personal, from both your missions? And my second question had to do with I believe it was just recently announced that the Russians are backing out from the ISS in 2024. It's just 2 years from now. Do you see this as a end of ISS or the beginning of the civilian endeavors? Thank you.
Okay, so the first question is, what was my biggest successes on the missions?
Biggest takeaways.
Oh, biggest takeaways. Okay, so I'd have to say from on my first flight, the biggest takeaway was that our mission was completely successful. And it was my first flight, and so not knowing how things were going to go in orbit, it was very, very satisfying that our mission was executed. Yes, we had a few things that didn't go quite right, but they were things that we could overcome, and we got the mission done. And it was, in the sequence of events, we were the first construction flight after NASA had a pause in shuttle flights because of the Columbia accident. And so with our mission is the construction of the space station was continuing. And so that was the big marker for our flight, was that we were the continuation of construction. And then after us, they continued expanding out the space station. On my second flight, the biggest takeaway was the fact that we could, in a year's time frame from when they had identified the issues with the rotary joint, from the time they first identified it, that they figured out what it was, came up with the repair plan, and were able to get all of the materials, the tools, and train us, the crew, so that we could launch and go execute the repairs. And in a time frame in 1 year to do that kind of a repair work, or that kind of an effort, is an extremely expedited timeline. And the fact that we got it completed, and shortly after our flight, they were able to put that rotary joint back into full operation. And so that gave the space station program the confidence that, yes, this is going to work. We don't need to go down the path of trying to figure out how they were going to replace this item in space, because, replacing a big metal ring, a big, 3-meter diameter metal ring in space is not an easy task. Also, the fact that you have to basically disconnect part of the truss element and then take the old one out, put the new one in. That was a huge effort, and the fact that our mission was such a success and put the space station back into full operation, they did not need to go down that pathway. And so those were the two big takeaways from my flights, that the work that we did up in space. The recent question about what came up, that the Russians were stepping away from the space station in 2024, which is what the current agreement is. NASA had stated that they would like to continue the space station until 2030. So right now, they're looking at, is that going to be the demise of the space station? It was built as an international effort with a number of different countries. The two largest partners, obviously, are the U.S. and the Russian Space Agency. And when they designed the space station, there were certain systems that they didn't duplicate between the two of them. And the biggest component that the Russians provide for the space station is for the attitude boost. And so if they come out, but that doesn't mean that we can't develop a capability to do that. It's just something that needs to be added. And so we would do that. NASA eventually would like to move beyond low Earth orbit, and so that's why NASA is now looking, we will continue with the space station until 2030, and at the same time we're looking at going on to the next place is going back to the moon, because even though we've been to the moon, we've never really lived on the moon. You go back and look, the Apollo missions, the longest one spent 3 days on the moon's surface. And so we're looking at building a habitat and having a permanent post on the moon, so that from there we can learn what is it that we need to do when we go further, whether it's to an asteroid, go to Mars, because, like I said, the preliminary plans is for a 2-year mission, and it's much easier to work out your plans on the moon, which is only going to take you a couple of days to get there, as opposed to going out to Mars and finding out once you're there that things don't work out because it's very difficult to get back. So we will move on. The good part about the International Space Station is that it was an international effort. And so for the past 20 plus years, it's been up in orbit and it's been functioning, and crews from countries around the world have been up there working together. And it shows you what we can do when, you know, you put politics aside and all work towards a common effort, a common goal. And hopefully we can do that again in the future, like when we go off to greater other adventures, because it is always much better when there are different groups working together that each brings some part to the whole equation, and then move on, as opposed to just one country trying to do an effort, or worse yet, trying to compete against each other.
The next question.
Good afternoon. I enjoyed very much your presentations, and I have 3 questions. One for Mr. Campins, which is, if you are not having, for now, any problem with satellites or comets or even asteroids, it seems okay. On the other hand, the problems with the garbage of the satellites that we send, and that are many of them garbage in the space, is there, you are going to have a problem sooner or later. The second question is to Heidemarie. When you made your space walks, did you feel anything about the radiation of cosmic radiation and solar radiation after so many hours of exposure to that, or no? And the third one is about the excess communication satellites that we have now, and is going to have some kind of problem or war about satellites and media, because of so many satellites, so many frequencies in the cosmic area and the air, about so many devices on there. Thank you.
Okay, well, I'll give you my take on the space. You call it the space garbage. We usually call it space debris, and it is an issue. It is an issue for other satellites, spacecraft, space stations, to have debris in space, because most things in space are traveling very, very fast. And when you have collisions, that's when you have a very bad day. For the space station, NASA protects a 5-kilometer zone around the space station. And so they track any object that's going to come within that sphere. And if need be, they will change the orbit of the space station, generally boost it up, so that they maintain that 5-kilometer kind of buffer zone around the space station. And then the concern about anything that they can't track that's out there is what they have to build into the design of the space station to be able to withstand any kind of debris. I know that coming back from space, both my missions, we took hits from space debris, and it was a smaller type. My first flight, it wasn't until after we came back and they did an inspection of the space shuttle that they reported to us that there was basically a pinhole on one of the panel doors that on the payload bay doors. And the hole was about 1/10 of an inch, so what's that, maybe 2 millimeters, 2.5 millimeters. So very, very small hole. And since the payload bay doors are not a pressure boundary and they don't seal, it's not a pressure boundary that needs to be maintained, and it didn't penetrate the crew module, didn't hit any of the equipment because the payload bay doors on the doors themselves are the radiators that provide the cooling for the entire shuttle. So no equipment was hit, we didn't hit any of the freon lines, no electronics, it was just a benign hit. They found it when they came back, and when they did an analysis of some of the debris around it, they were able to deduce that it probably came from a small chip from a circuit board from a satellite or some other spacecraft. So that's the size of a hole that we'll put it in. My second flight, I don't know, we were in orbit for maybe a week, and one of the crew members was sitting in the pilot's seat, and he looked out the window and noticed that there was a divot in the side windshield. And the divot looks just like the divot that you could end up on your car when you're driving too close to another vehicle and a rock hits your windshield. That was the exact same thing that it looked like on the window pane. Now the shuttle's windows are multiple paned, and the outer pane, the outer glass sheet, is just a scratch shield. Again, that outer one is not a pressure boundary, and it didn't penetrate it. It just put the little divot. It wasn't that bad that it sent a crack on it. It just looked like the little divot. And so the ground called us. We tried as best as we could from the inside, because it's not something we were going to go look at from the outside, because it's not an easy place to go on a spacewalk and get to. From the inside, we reported back to the ground, took pictures of it, and they weren't concerned about it because, like I said, the outer pane is not a pressure boundary, and it didn't look like it penetrated the glass completely, and there was no cracking that went through the glass. And so we were fine. But space debris does happen, and it is a concern. And the best thing to do is just to, we need to minimize it. And, shooting things in orbit to demonstrate that you can, you really need to think about the after effects and what to do about the debris. The shuttle and the space station is in a low enough orbit so that if there was, an errant satellite, like there has been, that it would take a while for it to get down to the shuttle's orbit or the space station's orbit, and then at that point, again, they would, based on predicted course, they could change the orbit of the space station to try to avoid that debris. Let's see, what was your second question?
The radiation in your body in the spacewalk.
Oh, radiation, yes, radiation on a spacewalk. So the radiation on a spacewalk is not something that we're going to feel immediate effects of, but not just for spacewalks, but for the entire duration of the mission. All crew members are issued a dosimeter that we carry around with us at all times, and that included going out on the spacewalk. The inner garments of our spacesuits actually has a little pocket for it, so we could put it there. And so the big thing from radiation is that none of the radiation that we see is damaging, that's going to give us any immediate damage, but the damage is something that they would see later on in life, because that's most radiation is going to give you problems later in life rather than unless you get a very high dosage, and we don't see that in space. And so it's something that is tracked and it's recorded, and there is a limit. We do have limits on the amount of radiation we can receive, and it's lifetime doses. And so if it looks like, we have had crew members, because in the early days we didn't have as precise measurements, and so they took averages that were a little more conservative, and there have been crew members that have been, in a sense, grounded because NASA came back and said, well, if you spent another 6 months in space, you would exceed your lifetime dosage, so you're in a sense done with flying in space.
We have a question, last question. There's someone, it was someone in the bottom there who is desperately asking, wanting to ask, and I think he's first, I'm sorry. No? It's this? Okay.
Hi.
Okay.
Hi. I have two questions. One for Ms. Piper, which is, when you're in space or on the walks, do you have a feeling of your position? I mean, what is up, what is down? Or is just... because the space, I mean, you don't know. I imagine that it would be difficult to know that position. How can you describe it?
Yes. You get very used to up being what's ever above my head, and down is by my feet. And quite often, we refer to things, what we'll say is the 1G orientation, which is the normal orientation that we see in training. And as far as getting disoriented in space, it doesn't matter if you're outside the spacecraft, the same thing happens inside the spacecraft, is you tend to forget which way is, the ground up and the ground down. And you have to start thinking about which way to move. And it's happened that because you're used to something in training. And so, okay, in training, I'm always, I need to go that way, so I always go this way. But if you start working on something, this happened to my crewmate, is that he was doing something and he just slowly ended up rotating himself, so now he was upside down. And so they told him to go down to the port side, and he started moving. And then somebody had to, because they could watch him from the inside, and they saw him moving, and they said, hey, Steve, wait a minute, you need to go to your other port. And because he didn't realize he was upside down. And the same thing happened to me in the space station. It's the same way, is that we normally look at the inside of the space station based on the way we normally see it in training. But there was one time I was going from the shuttle to the airlock, and you go through the US lab, and there were other crew members that were they were doing something at the robotic workstation. And so I just said, oh, I'm going to be clever. I'll just flip myself over and go along the ceiling so I don't bump into them. And then I'll remember when I get to the node, then the airlock is not going to be to my left, it's going to be to my right. So I did that. I got into the airlock, and I felt pretty proud of myself that I did the mental gymnastics to figure out where I was. And then I got into the airlock, and I was just looking around, and I saw all these bags. And I thought, why did somebody put all this stuff in the airlock? And then I looked around, and I realized I was looking at the top of the spacesuits. And I'm like, oh yeah, I'm on the ceiling. This is the stuff that's normally on the ceiling. Okay, flip myself around. Okay, now I'm good. So it happens all the time, and it doesn't matter if you're inside or outside.
So one last question from someone on the...
This is going to be tricky.
And we are approaching the end, I'm sorry.
Okay, so I'm a student and a climate change activist, and as scientists, I hope you both believe in climate change, and NASA and billionaires are very preoccupied. NASA and billionaires are very preoccupied with finding a new Earth, and they forget we already have one, and they do nothing to make it livable again. They're selling this idea but only to the elites, because a trip to space cannot be cheap, so us poor people would be left to die. So why can't the discoveries in space stay as discoveries for educational purposes and not for, plan B in case the Earth blows up? And does climate change increase our likelihood of being hit by meteors and asteroids.
Sorry, I am not sure if I got the question. If climate change?
I think I understood.
yeah.
Okay, okay.
So I'll address it if you don't mind. The climate change does not change the likelihood of being hit because the atmosphere is so thin compared to the size of an asteroid that can cause global devastation. So it doesn't really change. However, I do see a parallel between the threat due to asteroid impacts and climate change. They're both global threats, and they're both going to require international collaboration for us to address them. And they both have tipping points. So in the case of the threat from an asteroid, the tipping point is, are we discovering it before we can divert it, or have we discovered it too late and then we have to try to evacuate the area it's going to hit, or try something desperate? And in the case of climate change, there are these tipping points that we're hoping not to reach, but they are much more immediate than the long-term effects of climate change. So I see them as nicely complementary to each other.
And can I just give...
So it seems there is still one last question. Maybe let the very, very last question. One or two?
Hello, I am Martin. I'm currently a student, and I would like to ask a question to both of the speakers, if there is time.
Could you speak up? We can barely hear you.
Please.
I apologize. First of all, it's for you, Mr. Humberto. I would like to ask the steps that are necessary to maneuver a spacecraft accurately in an asteroid's uneven gravitational field.
That was the case of asteroid Bennu. The gravitational field of Bennu was about 100,000 times less than that of the Earth, but you still have to take it into account. And it changed because the distribution of matter inside of the asteroid is not even. So we did two practice runs of getting within a few meters of the surface and then flying away, so that we could understand all of the details that took for us to successfully sample. And so we had to do two practice runs, and we actually learned things in those two practice runs that we changed for. And one of them was the gravitational pull from the different rocks around it and inside of the asteroid. So all of that you can only figure out once you're there. So that's a very good question. It's a very difficult field to work in. And my colleagues in the navigation team of OSIRIS-REx, my hat is off to them because they did a wonderful job.
I thought it was one question.
My second question would be for Ms. Heidemarie. You spoke about the Artemis program, our return to the moon. I'd like to ask your current opinion on if it's sustainable. For example, the shuttle program got canceled because of the costs, so did the Apollo program. And I'd like to ask, with the current delays and unfortunate cost-cutting policies that Congress implements to NASA, if the Artemis program would be sustainable in the long term?
That will be an answer for a day.
What's that?
That will be an answer for a day.
Yeah.
Yes, I think so.
Well, since I'm not at NASA headquarters making this decision for funding programs, and definitely not in Congress making decisions for funding programs, that is one of the drawbacks of a national space program, is that you are at the mercy of the people that write the budget. And with the Apollo program, we did shorten the Apollo program. We had 3 more Apollo missions that were scheduled, that were, hardware was bought, and then funding was cut, and that was the end of the program. In the Space Shuttle program, it was a little more complicated because we had the Columbia accident, and because of the recommendations from the Accident Investigation Board, is that the shuttle was terminated, and cost was one of the issues, but it wasn't the same as in the Apollo era that the budgets were just cut. There were a number of issues that came out of the investigation board from Columbia that affected the space shuttle program, and high cost was one of them, but it was not completely cut from budget because of high cost, if that makes sense. There were also technical issues, and we had been flying the shuttle for a number of years, close to 20-some years by that point, which is much longer than we were flying any other program. And the shuttle was a reusable vehicle. And the original designs of the shuttle were to withstand 100 launches. But those 100 launches were supposed to take place in a time span that was much, much shorter than the 20+, and we were going to keep flying shuttle. So it's not the same to say, I can do 100 launches in 10 years, or I can do 100 launches in 50 years. Because there's other components that affect whether it's your airframe or your other hardware on board, other than just strictly the number of launches. And so all of those all played into effect, and that's what gave the recommendation from the board to finally retire the shuttle, because of the fact that it was expensive, but it was also old technology that was difficult to maintain. It was difficult to get replacement parts, and so that NASA would be better suited to focus on something other than the space shuttle. Also, the space shuttle had a lot of capability, which was critical and was required to building the space station, because you had the upmass ability in the shuttle's payload bay. You had a dedicated crew that went up with the shuttle, and that all could be dedicated to doing the construction required for the space station. At the time, only 3 members were on space station crew. You couldn't expect those space station crew members to do the same work as all of the visiting shuttles were able to build out the space station. But once space station was built, you didn't need that full upmass capability, so it made sense to focus on another vehicle, what we have today, that now we have SpaceX, and hopefully we'll have Boeing flying as well. So we will have 2 U.S. Carriers going to the space station. So lots of different things. As far as Artemis is, I don't know enough about what the long-range plans are for Artemis. One would hope that people planning the program would take lessons learned from previous missions, and one of the things with spaceflight is you also have to have an end game, so that you're not relying on an accident or a budget cut to define the end of your program. And so, with Artemis, that's going to the moon, but we still want to go beyond low Earth orbit and going beyond the moon, going beyond just our immediate, orbit, and go to another planet, another asteroid. And so hopefully that'll be enough drive that we go to the moon, build our habitat, learn what we need to learn, develop the technology so that we can use that as a stepping stone to go further.
Well, but we could continue to discuss, but we have to end this session here. So thank you all for coming. And as a reminder of our 2 speakers who think so much about space, but always having in mind also Earth, this is to put your feet on Earth. This is the socks with science.
Oh.
So we offer you a pair of socks. So that you remember when you are on the ground. This is something that we do with children to collect little seeds, little pollen, all the wonderful things that make life on Earth so nice, and that maybe we will find in other planets, who knows. But until then, you have these socks. So thank you very much. Thank you all for coming.